Hi, I'm Bjorn Therese, and I'm here to continue my video series on process control. In part 1 of this series, I introduced a simple process with two water streams mixing into a large tank and providing an exit stream of a specified temperature. We also calculated the steady-state gain of this process. In this video, we continue to understand the process, but now we look at the dynamic aspects of a response. I mentioned in part 1 that the ion exchange column and the tank inventory are the dynamic elements of the process. We will see how these affect the time response of the tank temperature after changes to process inputs. In preparation for the first open loop test, we set the tank temperature in manual mode and set the tank level controller set point to 95. We also go into the config menu and adjust the amount of packing in the ion exchange column to give us 0.2 hours of dead time. We now set the process to steady state by giving the output of the temperature controller a value of 34.5. This will fairly quickly line out the process, and the tank temperature is going to be 50 degrees. I also want to do a couple of other things. The charts that we see here, I want to get rid of and introduce two new charts. To do so, I go into the Edit menu and click on the two charts and click on the wastebasket and then click on Done. And after that, I go to the Charts button on the tank TC and I get two new charts. One is the temperature in the tank itself, and the other one is the output from the heater. And that is the temperature of that stream. So now I'm ready to make a step change. I'm going to type in an increase of 30% on the output of the tank temperature controller. So I'm going to put in 64.5. But before I hit enter, actually I just did it, at the point where the chart had scrolled to the end of the cursor scrolled to the end of the chart, and now I get a very clear delineation of where the response started at 10 hours here. And you can see there is a slight delay in response of the temperature after the input has changed, and then followed by a first order lag or response where the temperature is gradually gliding up to and ending up at 62.9 degrees, which is the final value after this input. So I'm going to make some more changes. I'm going to set the output of the tank temperature controller back to 34.5, and that way I get the temperatures to go back to 50 degrees. Change the dead time from 0.2 to 0.05 hours, and then perform the test again. And I have saved previously these charts or outputs, so we'll come back to them and analyze them in a little more detail. But for now, we're just doing the tests. So I'm going to set the tank TC to 64.5 and wait to hit enter key when the line has reached the end of the chart at 18 hours, right there. And now you can see the amount of dead time or delay before the tank temperature starts to change is much shorter than it was before. The tank temperature climbs up to it's the same final value of 62.9 it's going to end up at, and the overall response after the dead time or the initial lag is the same. So we'll do yet another test by typing in the 34.5, getting it back to 50 degrees. This time I'm going to change the tank level to 5% instead of the 95%. This means that I have very little water in the tank, and you will see that that affects the response. I still have the short dead time in the process. So at this point, it's pretty much lined out. And go in and type in 64.5, and well, I guess I just missed the time point there of 24 hours, but I'll catch the 25-hour time point right there. And now you see that not only is the dead time very short, but the following so-called lag is also very short, and the process output or the tank temperature comes up to its final value in very short order. All right, so for a final test, I'll bring it back to 50 degrees first, and then change the dead time to 0.2 hours. And then we'll do the test again. 64.5, and catch it at 29-hour point here, right there. And now you see there's a long delay in response, and a fast climb goes up to 62.9 degrees in very short order. So I've shown 4 different tests here with quite different responses as far as how they respond in time. And now I'll go back to those and analyze them in a little bit more detail and see exactly what these things mean. Let's start the analysis by the response from the first test that we made. There are 3 things we're interested in deriving from this response, namely the dead time, the time constant, and the steady state gain. We start with the dead time. The dead time is the distance in green here between hour 29, when we made the step change, and the time by which the temperature started to rise in the tank. We can see that this distance is roughly 0.2 hours. So I'm going to write in D, 0.2 hours. That's the dead time. It essentially means that for 12 minutes, nothing happens after you make a step change in the heater input. The second parameter we're interested in is the time constant. And the time constant is the distance in orange here between the end of the dead time period and 63% of the final response of the temperature response, 63%. And that, in this diagram, appears to be around 0.3 or slightly more than 0.3. Theoretically, it's 0.35, so we'll just write that in. So those are 2 parameters that we're interested in. The final parameter that we'd like to have is the steady state gain. We see here on the curve that the steady state gain is temperature goes up by 12.9 degrees. And it does so for a change of 30% on the output from the controller, that is the input to the heater. So we can say that the steady state gain is Kp equals to 0.129, where I've divided this 12.9 by 100, which is the transmitter span, and divided by the 30% change that I made on the controller output, and this happens to be 0.43. The same value, of course, as we derived in the previous video. Okay, so those are 3 important parameters, and we yet have another parameter that is derived from these 2, and it's called the dead time to time constant ratio. And I will put that right here to make it clearly visible. So dead time to time constant, in this particular case, it's 0.2 divided by 0.35, and that is equal to 0.57. Okay, let's move on to the next response. In this response, we retained the time constant. You can see here the fairly long time constant, but we shortened the dead time to a mere 0.05 hours by having a much shorter ion exchange column. The steady state gain is the same as before, so no changes there. And the dead time to time constant ratio in this case is therefore 0.05 divided by 0.35, and that's equal to 0.14. The third response is one where we had a very small dead time and also had very little level in the tank, so we ended up with a very short time constant. The gain is the same as before, but the dead time to time constant ratio is now 0.05, which is the dead time, divided by, you can show, this is fairly easy to calculate. I'm not being able to read it off the diagram, of course, but it's 0.018 time constant, and the ratio here is 2.7, larger than before. And the final case that we looked at was when we had a short time constant here, but we arranged to have the long delay in the ion exchange column, so we have a long dead time. and the time constant, the dead time to time constant ratio in this case is going to be 0.2 divided by 0.018, and that is actually 11. So a very large ratio. Okay, that really concludes the analysis of the step tests, and we'll be able to use these pieces of information, namely the steady state gain, the dead time, and the time constant, and also throw in the dead time to time constant ratio as we analyze controller performance.